So next question is on group 4 elements. So carbon all the way down to lead. So there's one structure and bonding. So typical thing. So we got to start the structure first. So diamond has giant molecular structure, which I hope you know as part of your case study. Diamond versus graphite. Okay. So what are we breaking? Okay. So melting diamond required. Well, melting diamonds requires breaking your covalent bond. So many strong covalent bond. In this case, it's just carbon-carbon covalent bond. Therefore, lots of energy is required. If you require a lot of energy, therefore, very high melting point. Okay, so use the information in the table to suggest how the structure and bonding in diamond differs from the type of structure in tin. Okay, so I do not need to specify all of this again, but I might need to compare them to the structure and bonding in tin. All right. So I hope you can see that diamond, the melting point is around 3000 plus. Tin is around 200 something. Okay. In comparison, these are considered low melting point. This is close to 1000. These are considered high melting point. Okay. I would consider this to be simple structure, simple molecular structure. Okay. So the very much lower melting point of tin, 232 degrees Celsius, in comparison to that of diamond, which was 3550. Most likely tells us tin has simple molecular structure. Okay, and if you have simple molecular structure, therefore melting tin, melting tin, it can't really have a simple molecular structure, can it? These are what we consider metals. So I guess you can say the metallic character increases. I really wouldn't be comfortable calling it simple molecular then. Maybe it is not this. I can probably call it giant metallic. Okay. What do you think? It's a giant metallic structure. Okay, so we know the metallic character of the metal itself increases down to group 14. So if there is giant metallic structure, then we are talking about breaking only the metallic bonding. So melting tin only requires breaking strong metallic bonds, which you saw in earlier part of the question, is about breaking the electrostatic force of attraction between the cations and the sea of delocalized valence electron, which does not or do not require as much energy as breaking covalent bond. Okay, hence you have lower melting point. All right. Tell you that silicon is a giant molecular structure, which you should know. Okay, similar like the structure of diamond actually. Okay, physical properties. Well, you can talk about high melting and boiling point, because if you know how to explain the high melting and boiling point of diamond, we are talking about breaking covalent bonds, right? The actual covalent bond is actually quite strong, and you have to break a lot of it in this giant molecular structure. Okay, and what other thing you can talk about? well, it doesn't conduct electricity as well, okay? So it has the same structure. It has the same structure as diamond. I think this is actually your case study, yeah? Oh, I spelled diamond wrongly then. This is your case study, meaning something you have to know from your O level, okay? So it is actually does not conduct electricity, or you can say it's a poor conductor of electricity, all right? So does not conduct electricity. Actually, that is a poor choice of word. Silicon is a poor conductor. Electricity is correct, because silicon actually is used in semiconductor industry. Yeah, so I wouldn't go away and say it doesn't conduct electricity. It does a little bit. We use it in chips, you know, microchips, okay, in transistors, because of their semi-conducting property, but they are really poor conductor, right? But you can obviously associate diamond being very hard, so physical property of it will also be very hard as well. And this does not dissolve in water. This won't dissolve in water as well. Okay, so here you want the dot and cross. You need to show the outer shell electrons. If I were you, I would be thinking carbon is above silicon. So they will have similar number, well, they have the exact same number of outer shell electrons. And I know how to draw CH4. I mean, that is my CH4 display formula, where I show the bond. Each bond is a covalent bond. Each covalent bond involves one electron from here and one electron from there, and hydrogen only has one outer shell electron, so you use the only outer shell electron for that. There is no outer shell electrons on the hydrogen. Now convert that to silicon. What do I have? I'll have dot cross, dot cross, dot cross, dot cross. Hydrogen, 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 hydrogen. End of story. Now you say, well, you see, dot cross, cross dot. Does that work? These are electrons, okay? Whether they are dot or cross, they are electrons. Electrons are electrons. The whole idea of drawing this dot and cross to students, okay, or whoever, is so that you know that one comes from each one. By the time they are bonded, you can't tell the difference. Electrons are electrons, okay? This is a normal covalent bond because one comes from silicon, one comes from hydrogen. We don't show two cross or two dot, right? The other thing is, some people like to draw shell. I personally do not like to draw shells. Doesn't matter, it's a personal preference. This would be correct, drawing the shell would be correct as well. I just find it tedious. I'm a bad drawer of diagram, so I would be very messy if I had to draw shells, okay? Next bit, we need to talk about structure and bonding. Why silane? Silane was SiH form. Is this molecule that you just drew there. The information they give you is it has low boiling point, okay? So low boiling point means it boils easily, okay? Means SiH4 must have simple molecular structure, okay? You mentioned the structure already. Now you need to talk about what you need to break when you boil it. There's liquid to gas boiling. What happened? Well, I can't spell properly. What happened when you boil silane? What happened? Okay, so for boiling SiH4, so liquid to gas, we need to break not the covalent bond, basically not the SiH covalent bond, but the weak intermolecular forces. So you need to specify that the covalent bond is actually strong, but here you're just breaking the weak intermolecular. Inter refers to in between, molecular because, well, they exist as simple molecules. So you have SiH4 and then the next SiH4, etc., etc. The weak intermolecular forces between SiH4 molecules, plural because you have more than one molecules, yeah? These don't require a lot of energy. These don't require a lot of energy, therefore low boiling point, okay? Next bit, they want you to compare, describe two similarity between silicon dioxide structure and diamond. So diamond, you have carbon, 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 like that, 1, 2, 3. So each carbon forms 4 bonds. Like that, it forms a framework like that, okay? So think about like silicon, also the same, yeah? I can tell you that silicon, it's not in your syllabus, but silicon looks like graphite. that is not silicon dioxide, that is silicon. In your group 4, you have carbon, silicon, germanium, blah blah blah. 4 outer shell electron, right? Same structure, giant molecular structure. This is silicon dioxide. What has happened? You have an oxygen in between each silicon. Each silicon is still bonded to 1, 2, 3, 4. Each carbon is bonded to 1, 2, 3, 4. This is diamond, this is not graphite. I'm just showing you this to compare the structure, but you just need to know this and this for this particular question. 2 similarity. Each silicon is bonded to 4 other oxygen atoms. So there is 4 single covalent bond. Okay, just like each carbon is bonded to 4 other carbon in not graphite, diamond. Alright, then they want the similarity in structure, they don't want in any other property. So that's one I could think of. What else? What else could I think of? Oh yeah, I did mention it just now. So both SiO2 and diamond have giant molecular structure. Yeah, I mean, that's pretty obvious. What else could you say? I mean, I did mention that each of these is a covalent bond. 1, 2, 3, 4. Each of these is a covalent bond. 1, 2, 3, 4. It is pretty much implied from here really. When you say each silicon is bonded to 4 other oxygen, so that means there are 4 covalent bonds there, and each carbon is bonded to 4 other carbon, there are 4 covalent bonds. So it's kind of together in this package already, yeah. But I mean, this is probably the obvious one, like just by stating the structure, both of them are giant molecular. Next bit is a standard question. Why does it have high melting point? So SiO2 has, well, in fact it's repeating whatever we have written before. So we always state the structure first. So when you have giant molecular structure, what does it involve when you melt? Melting SiO2 requires breaking many strong covalent bonds. But which covalent bond are you breaking? You're breaking the SiO covalent bond. Therefore, very high melting point. Structure of a compound of silicon. Deduce the molecular formula. So total up the number of atoms in one molecule of the substance. There's the definition of molecular formula. Carbon, 1, 2, 3, 4. Hydrogen, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oxygen, O2, 2 oxygen there, and don't forget the silicon. Okay, draw a dot and cross for silicon 4 chloride. Silicon is in, before I do this, I should probably think back on carbon, silicon, germanium, blah blah blah. This group 14. 4 outer shell electron. Okay, what do you know? You know that chlorine usually forms single covalent bond. So single covalent bond. I would draw display first. This is called display formula. Display formula is where I show all the bonds. Why did I start from here? Because I know it's very easy to get it correct. Silicon, like carbon, form 4 covalent bonds. 1, 2, 3, 4. Silicon has 4 outer shell electrons. It has used 1, 2, 3, 4 for bonding. There is no other electron on silicon. Chlorine is from group 17. When it forms covalent bond, it forms single covalent bond, but it still has 1, 2, 3, 4, 5, 6 other electrons that are used for bonding. So 6 other electrons, 6 other electrons, 6 other electrons, 6 other electrons. Now I can confidently from here, I can draw, if I sketch this first, I can now draw the outer shell electrons for dot and cross. Silicon, dot cross, dot cross, dot cross, dot cross. Chlorine. Each of these is 2 electrons. It's a covalent bond. shared electron, one from silicon, one from chlorine. This is not correct because you want to show outer shell electrons. Chlorine has 7 outer shell electrons. That's the danger of this diagram. It does not show you the electrons on the other thing. Yeah. So if I say dot is silicon, then cross is chlorine. So remember I said there are 6 on each chlorine. So 6 electron. Just like that. It is so much easier once you get this. It gets tedious when you start from here and keep on rubbing and keep on drawing and stuff. Another thing that people like to do in O-level, I know, because you are taught to do so specifically, is to use shell. Perfectly fine, perfectly understandable, would be correct. What is wrong with this? I didn't show the exact shell, but is this diagram wrong? I have shown dot and cross. I have shown all the outer shell electrons. I did not use display formula, I used dot and cross. Is this wrong? This is not wrong. I mean, it's perfectly fine. You will see some books actually show this, and you will not be penalized if you do this. However, I would advise you, if you're in school, talk with your teacher and think about possible answers that can be accepted, and I guess just do whatever best suit you, really. Okay. Okay. Next bit, SANE, so you want high melting point. So SANE is SiO2 there. So SiO2 has a giant molecular structure. Okay. So we talk about the structure already. So we need to think about melting. So melting SiO2 requires breaking many strong covalent bond. In fact, what will make your answer stronger is you talk about covalent Si, strong Si or covalent bond, okay, in the context of this example, okay, therefore, very high melting point. In case you're not aware, you should know the structure of SiO2. Each silicon is bonded to 4 oxygen, and each oxygen is bonded to 2 silicon, just like that. Each oxygen is bonded to 2 silicon. And each silicon is again bonded to 4 oxygen. And this network continues on and on and on. It's a giant molecular structure. So melting a giant molecular structure means you have to break each and every one of these silicon-oxygen covalent bond. That requires a lot of energy. Yeah? Requires breaking many strong covalent bond, which require a lot of energy. Which needs a lot of energy. Therefore, very high melting point. Okay.